random numbers. We didn't do it, but you will see that it's quite similar to what we did yesterday. I wanted to talk about another way to generate samples in statistical mechanics, and this is Newton's equations. Now, just to summarize here, I've written why are we allowed to use Newton's equations for particles. Well, we can study this de Broglie relation, and this tells us that the de Broglie wavelength for everything that is heavier than, say, hydrogen or H2, the de Broglie wavelength is small enough, and I can use classical mechanics. So instead of having to deal with quantum numbers, I deal with positions and velocities. And we use the same word. If we know all positions and velocities, we use the word state. Like when in quantum mechanics we know the wave function. So here I've written de Broglie again in small. Well, here I've just written MV, and I've not taken advantage of the fact that I can take MV from the kinetic energy. Okay, so there is one more thing that we have at least to mention, and this is that we do also our statistics classically, which means we completely forget about the spin. Okay? So in our statistics, spin that is still there, and we know that the spin is something really quantum mechanical, and we cannot find some equivalent in classical mechanics. So we just forget about the spin. Now, what are the conditions to forget about the spin? And the conditions that are written here, it is that we have, when we think spin, we have to think quantum mechanics. So we think about quantum mechanical states for a second. And what is the problem with the spin? The problem with the spin is Pauli's principle, that you are not allowed to put more than 2 spins in a state as we defined it. Now, the argument here is that you have many, many, many more microstates than you have particles. And you have millions and millions more microstates than you have particles. So the probability to put 2 spins like this, or maybe to put 3 spins in one state, is very, very low. Okay? So we do statistics in such cases that there are many, many more microstates than there are particles. And this is typically true at high temperatures. At low temperatures, or for some very specific systems, like electrons in a metal, this is not true. This is why electrons in the metal, they obey another statistics which is called Fermi statistics. So Fermi statistics is statistics where you take into account that particles have spins and cannot populate the states as they want. They can populate the states only as long as they obey Pauli's principle. We will not do that. And then there is another type of statistics which is called Bose-Einstein statistics. And Bose-Einstein statistics holds for particles where the spin is not 1/2, but where the spin is 1 or 2 or 3. There are such particles and they are called bosons. So if somewhere in a book you see the terms Boltzmann statistics, you know this is statistics where the spin is not taken into account, where the spin is forgotten. And if you see Fermi statistics or Bose-Einstein statistics, you know that the spin plays a role. Who was Fermi? Enrico Fermi. He's famous for building something that was called the Pile in Chicago. And that was the first nuclear reactor. So Enrico Fermi is maybe not the inventor, but the person who first built a nuclear reactor, like you have today in every nuclear power plant. And Bose was an Indian theoretical physicist, and sometimes people call it Bose statistics, sometimes people call it Bose-Einstein. I don't really know who did what. Okay. So here I summarize again what I've said before. You know, we have very, very, very many microstates and only very few variables that characterize our macroscopic observable or our macroscopic system. And for that we have Gibbs phase rule that tells us how many such variables we have. And this is also has been said, but this will be important today. Where did the mouse go? Here it is. We can construct a vector that contains all positions and all velocities of all particles. For instance, at a given time t, and that we call the classical state of the system. So you see this is a big vector. If I have 100 particles, and each r is 3 and each v is 3, so that's a 6n dimensional vector, so it would be 600th dimensional vector. Well, mathematicians and computer don't care whether it's 3-dimensional or 600-dimensional, exactly the same thing. Okay, so here I've taken this, I think, from Patria's textbook. It says there are more microstates in a glass of water than stars in the universe. Maybe there are even more microstates in a glass of water than atoms in the universe. So this Boltzmann statistics is a pretty good approximation. The probability that you will put two spins wrongly in the same state is virtually zero. Okay, so this is where we stand. We have the Born-Oppenheimer approximation. Okay, and here I've again written something about, how should I say, coarse graining. Let's not dwell on this too much. And this we have already looked at. So these three partition, or 3 or 4, or how many partition functions that you want. The canonical partition function, you remember, that's the one when the temperature is constant. So I have different energies and I have to look at the probability. And of course, what I want to do is to find first the states I that have a large probability. You would not start with the ones that are very unlikely. Okay, and for this partition function, of course, there are relations between the partition function and observables. So here I've written the relation between the canonical partition function and entropy, but you can also write the same for the average energy. Only average energy, because the energy changes, the energy fluctuates, right? I fixed the temperature. So I fixed the number of particles, the volume, and the temperature. So I cannot fix the energy. The energy will fluctuate. But, of course, the average value of the energy, that will be constant in an equilibrium system. So this is why I write here, I compute the average value of the energy. And you see that it's quite simple. You take the logarithm of this thing, and that's okay. Then here I have some discussion about equilibria, and I think I will do that next year. Okay, this equation, or these two equations are important because they tell you if you have some property of the system. So A is a property of the system. Maybe the pressure, or maybe viscosity, or maybe the X-ray diffraction, or the neutron diffraction, or NMR something, or whatever you want. So A is an observable. And of course, for each configuration in your system, the observable is different. I mean, you know, the particles are at different positions. So maybe the X-ray signal will be different. Right? My particles are like this and my particles are like this. X-ray signal will be different. And so I have to do averages, and this tells you how to do the average. And you see that the partition functions, they appear simply here in the denominator. So just remember that when I understand these expressions here, so here I have many energies, so it's exponent. Here I have only one energy, so it's the delta function. And I've written the way physicists write it very often, that I've said all positions I'll call Q, and all velocity or momenta I call P. So in many textbooks you will find that they write dp dq. So dp is dp1, dp2, dp3, dp4, and dq is dr1, dr2, dr3. So not to have to write so many variables here, and also not so many integrals here. Very often you find this shortened notation. And you see, this is just like you compute averages completely normally. If you say this and the normalization factor is the probability, then what it says here is just A average is A multiplied by its probability integral over everything. So this equation is not at all mysterious. It is just the equation how to compute averages. Any average if you know the probability, like you did in high school. Okay, so this is somehow where we want to go, what we want to do. Okay, here I have something about equilibria, isotope equilibria, blah, blah, blah. We'll do that next week.
And in the formula before, you have this integral over the P and the Q's, and that is exactly the reason why we do the Monte Carlo method, because it's so many P's and Q's, so it's many dimensions.
Yeah, this is the integral you want to do with Monte Carlo. And remember, if you have 100 particles, you have 100 p, so 103 dimensional vectors, so 300 px, py, pz, and you have 300 q's, and so this is basically 600 integrals. It's a 600 dimensional integral, which is a bit cumbersome. And you have 1 million particles, it just becomes more cumbersome. Okay, so basically all it boils down to is that we need to know the P's and Q's. We need to know the configurations. And not just one, but many, and preferably the important ones. So we have two tasks: find the P's and Q's, but not some very crazy P's and Q's, like in my example, one particle going very fast in one direction, all the other ones not moving. Our task is find configurations, find states that that are likely to contribute a lot to this integral. So where this factor here is, oh, I forgot the minus sign. It depends how you write it. Usually you have a minus sign here. If you write your energy positive, you have a minus sign because, of course, you want this to be smaller than 1. Okay, so Monte Carlo is one way and molecular dynamics is another way. And I assume that all of you would know about integrating Newton's equation, but this is not the case, so I have not written anything here, I think, and I will have to do it on the blackboard. Okay, let's do it on the blackboard. Problem is that I have to stand. Okay, so the basic idea is that we have particles. And we have to start somewhere. So you know that Newton's equations are differential equations. When you want to solve differential equations, you need initial conditions or boundary conditions. Okay, everybody knows that? If I have it, what is the solution of a differential equation? Any differential equation, what is the solution? Maximum? I have some differential equation. I don't know, some differential equation. X dot equal f of x. What will be the solution of this? Is there only one, or are there many? Only one? Okay, let's. What is x? Well, I should write x times t so you see it. Or maybe I can write. Well, let's write x dot and let's write here cosine x times t. So I'm looking for x where the derivative of x is cosine. Which function has a derivative cosine? Sine. Okay, so x of t equal sine xt is a solution of the differential equation. Is that the only solution? No. What other solutions are there? Well, this would you're thinking about specifying boundaries. Okay, yes, you could do that, and then depending on the then when you specify the boundary, or let's put it the other way around, can you specify any boundary you want? Or does this work only for this or this?
Only works for this.
Only one boundary possible?
If you select your boundary, your result is gonna belong to only.
That's right. Absolutely. That's correct. If I select a boundary, then my result will apply only to this boundary. But my question was, can I select any boundary? Of course, yes. And this means here, if we look at this problem, that I can add a constant. Because if I derive the constant, it disappears. Right? If I take d dt of this, I get cosine plus 0. So a differential equation has equations for solutions, right? The solution of a differential equation is an equation. Okay, and this is why we need boundary conditions or initial conditions. So let's say this is my initial condition. Now, of course, the initial condition requires, since it is a second order differential equation, I must give the positions and the velocities. It's not enough to give the positions. So let's specify some velocities. So this would be my initial condition. Now, what do I know about this system? Well, I know there are classical masses. So I have M1 and M2 and M3 and M4. And for each of these masses, I can write Newton's equation. So what is Newton's equation for mass number 1? Well, Newton's equation for mass number 1 equal force acting on mass number 1. You see, the acceleration is a vector, and the force also is a vector. So this is a vector equation for particle number 1. And I can do exactly the same for all other particles. So 2, 3, 4, let's write it for 4. Mass number 4 times acceleration of particle number 4 equal force acting on particle number 4. Okay? Now, if we know the force, let's just for 1 second, but only for 1 second, think we know the force on particle number 1. Then we can, what mathematicians call, integrate Newton's equation. This is, we can, with some mathematical trickery, but from this, if we know force number 1, we can say R1 of T equal something. I don't know, equal R1 maybe of 0 plus V1 of 0 times T plus something. So at the end, that's what we want. I mean, this is what we want. We want to be able to say if the particles are as described in my initial condition, they will move, they will follow a certain curve in space, and this is called the trajectory. So let's say this is my particle 1, and maybe it moves some This would be the trajectory of particle 1 if the force changes in some way. What is the trajectory if the force is 0? That is something you know. What is the trajectory of a particle if the force is 0? Dot? What is the trajectory of a particle that has some initial condition, that has some initial position and some initial velocity, but the force is 0? So it's a particle with some velocity in empty space. There is absolutely nothing that makes a force on this particle. How does the particle move? Does it stay put, just doesn't move, or what does it do? That's right, it just continues, makes a straight line movement. That's what's called inertia. Maybe it's called first law, yeah. So a particle without any force acting on it will just stay or continue the movement it is doing before, and the movement it's doing before is just flying with v equals 0. So our trajectory comes from this inertia plus from the fact that the particles interact. Okay, so come from the force. So let's look again at particle 1. What color could I use? Black. So let's say particle 1 interacts with particle 2. So there will be a force. Maybe they attract. So there is some attractive force here and here. But maybe it also interacts with particle 3. So there is some attractive force here and here. And maybe it also interacts with particle 4. No, that was 3, 4. But that's far away. So maybe the force is just much, much smaller. And you know, when there is a force acting between two particles, it is the same, but with opposite sign acting on each particle. That's also called Newton's zeros law or something like that. Or second, I don't know, Newton's something law. That's right, action equals reaction. Actio equals reactio, Newton said, because he wrote his book in Latin. Okay, so of course what we would do then, we would just, add up the forces like you have learned. You make the force parallelogram and you just add up your forces, and the total force acting on particle 1 would be something like my big black arrow. Right? Forces are vectors, and when you have two forces acting on one particle, well, you just add the two forces like you add two vectors. Okay, now these forces here, I have just drawn them like this. But if these particles M1 and M2 and M3 and M4, if they are molecules, where do I get the forces from?
Intermolecular force. Intermolecular force.
Intermolecular forces, or intermolecular potential energy surface. So, I have an intermolecular potential energy surface, maybe V12, maybe it's a Lennard-Jones, so it would be A12 divided by R12 12 minus same thing 6, and maybe I have a V13, and maybe it's different because the particle 2 is a different particle from a different chemical species than particle 3. So I have this potential energy surface. How do I get the force from the potential energy surface? How do I get the force from the potential energy surface? How do I get the Coulomb force from the Coulomb energy? How do I get the gravitational force from the gravitational potential? It's always the same story. How do I get the force from an energy? Yes. Differentiate how? The force is a vector, right? So we need some of the potential energy. That's a scale. That's a number. You know, so many kcal per mole. Differential operator? Differential what? What is differential momentum? Yeah, but to get the force from the potential, your derivative is taken with respect to the position, not with respect to the time.
Differentiate by position.
That's right. And how is this called when you you have a value and then you differentiate to get the x and to get the y and to get
Gradient.
gradient, that's right. That's right. So we take this thing here and we write this is minus the gradient. How do you write? Do you write grad or do you write nabla?
I write a triangle.
Nabla, okay. So minus nabla, and this is a vector of v1, 2, and here sometimes you write a little 1, which means that you do the derivative with respect to the coordinates of particle 1. So d dx1, d dx2, d dx3. And of course, since I have many forces acting on this, I also have to do minus derivative with respect to coordinates of particle 1 of v13 plus derivative vector with respect to the coordinates 1 of v14. So this is adding the forces, right? The force between particle 1 and the force between particle 2. Why did I say minus here? Of course it's plus force coming from particle 4. Okay? So all this is mathematics and can be done. Right? Your computer can do that quite easily. It costs a lot of time, there are many computations, but you can do that. So at the end, I really, now I can simplify it again, and I call this again F1 like I did before. Now I know where F1 comes from. It is just the sum of the gradients, force acting on particle 1. Now the problem that you have here is that, you know, when particle 2 moves, the force on particle 1 changes. And the force on particle 3 and 4 also. So these forces, the force on each particle depends on all other particles. And this is why we say these differential equations are coupled. They are coupled together because equation number I depends on all the other equations. This is something that we have already discussed when we talked about electrons. What did we say? We say, well, if we have an atom with many electrons, of course the Hamiltonian says that the energy depends on the distance between the two electrons. or 3 or 4 electrons. So when electron 2 moves, this changes the interaction with electron number 1. And when electron number 2 moves, that changes. And so they're also coupled exactly in the same way. And what trick did we do for the electrons? How did we solve this problem that everything depends on everything?
Field.
Yes.
Mean field.
Mean field. Exactly. This is when we do the mean field approximation so this Hartree treatment and self-consistent mean field treatment. And here comes the big problem. In classical mechanics, you cannot do mean field. People have tried, you can find some paper where people have tried exactly the same trick and have said, well, I will assume that the particles 2, 3, and 4, they just make some sort of average, and then I study particle 1, and I will try to make that self-consistent. And certainly for chemical problems, so for problems where the masses stand for atoms and molecules, this does not work. So mean field treatments, I don't know in astronomy whether they can get anywhere. Maybe they can treat galaxies as a mean field, I have no idea. But you see, here I say these masses, they are atoms. If I were an astronomer, I would say there are planets or moons or comets, or if I'm in the military, I say there are rockets and drones and satellites. It's exactly the same thing. And I have a story about that. It's true. When I was a little bit older than you are, I was a postdoctoral fellow in California. And we worked already at that time, that's 40 years ago, we worked on things like this. And one student, he graduated, his PhD was about such molecular dynamics simulation. He graduated and he went to work for a company called Raytheon. You know Raytheon? Big military company, making rockets and making airplanes and I don't know. And so half a year later, he came to our lab and we said, Steve, what are you doing? And he said, oh, secret. I cannot tell, very secret. But I can tell you, I'm doing exactly the same thing. So he was doing such classical dynamics, except not for molecules, but what they were actually trying to do at the time is when the Russian rocket came and they wanted to shoot a rocket and shoot it down. This was under President Ronald Reagan and it was the very big thing. So these methods are quite universal, and the problem is a problem that we have seen already in quantum mechanics. The problem that we have here is that this mean field approximation does not work for chemical problems.
Well, it does not work in the sense that you take one particle and look at the mean field of all the others, but it works maybe a little bit in the sense that, for example, for electrostatic interactions, you can say these particles in some box far away, they are just a dipole moment or a multipole moment or something like that.
Yeah, that's true. I mean, you can use multipole expansions sometimes. Electric engineers, do you know about multipole expansion? Monopole, dipole, quadrupole? No? No? Okay, we will talk about this maybe next year. Okay, all right. So this is where we stand right now. We have written down the problem. The problem is a set of second-order coupled differential equations. So this would be a set. Set because I have many, here 4, of second order. Second order because I have here a second derivative with respect to the time. Coupled because the forces F1 depends on 1, 2, 3, 4, F2, F4 depends on 1, 2, 3, coupled differential equations. And we need to find the trajectory. So what we would like to find is, well, particle 1 moves like this, and particle 2 starts here, but particle 2 maybe moves like this, and particle 3 was here, so particle 3 maybe moved like that, and particle 4. You know, this would be the trajectory for our system. This would be somehow to know if the particles start with the initial conditions that we have, how will they move? How will they dance with each other? You know, they interact, they attract, they push each other away, they have kinetic energy, so they have inertia, and how will they move? This is the trajectory. And this was a big problem in astronomy. They were trying to find the trajectory of Sun, Earth, and Moon, and other planets. And they studied exactly this problem, except without computer. And as I already told you, they found that they cannot do it. I mean, they tried this, and they tried that, and they tried introducing new variables, and it helped a little bit, but not really, and at the end they decided we cannot do it. And then there came a mathematician, Henri Poincaré, who demonstrated it cannot be done. You cannot find the trajectory of such coupled second order differential equation. And Poincaré demonstrated, I don't really know how, but he demonstrated really that it is not possible. The fact that it is not possible has to do with a phenomenon that will become at some point important for us, that's called chaos. What do you know about chaos?
Big disorder.
Yes? And mathematically, what does it mean? If a system is chaotic. I mean, chaos is a mathematical word. It's not just a political word in Bangkok and elsewhere. It's a mathematical word. You never studied in mathematics? Well, maybe they call it non-linear systems. Yeah, non-linear systems, that sounds familiar. Yeah? So non-linear systems make chaos. And what it means is, let's look again at only one particle. So I take again particle 1, that was green. So I take particle 1 and maybe, you know, it makes a trajectory like this if I use these initial conditions. Now I change the initial conditions, but very, very, very little. Right? I change maybe the direction of the initial velocity by 0.001 degree angle or something like that. what do you expect the trajectory will do? What?
Very
Same, very close. That's what everybody expects. And these equations say sometimes not. Sometimes if you change the initial conditions very, very little, the trajectory will be completely different. So such systems, they are super sensitive to your initial conditions. And this is why they cannot really be pre-computed. You probably heard about these things that, you know, people say if there is a flea in Peking and the flea does something, that the weather in Bangkok will be different. Butterfly, right? Butterfly flaps its wing and the weather will be different. This is this, you know, when the butterfly flaps the wing, it does change the initial condition a little bit. Now, most of the time, it doesn't have any influence and the trajectory stays pretty much to what it was without the butterfly, but sometimes it changes completely. And this is why we cannot really compute, we cannot find a mathematical equation, we cannot find a formula for the trajectory. We cannot write R1 of t equal cosine blah 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 plus exponential function blah 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 plus, we cannot do that. Now you know that this is possible because people know how to compute trajectories of rockets or trajectories of satellites, and so it must be possible to do something. It must be possible to predict the trajectory, and the answer is you have to do it numerically. And this, I think, we will study next year. So the important thing is that if there is this coupled here, you have to find your trajectory numerically. You cannot solve it. But I mean, it's the same for the psi function, right? If you write your psi function as a sum of basis functions, it's also numerical. I mean, you cannot write psi of x equal something, right? You write psi of x is a little bit of this function plus a little bit of this plus a little bit of this plus a little bit of this. So this idea of doing things stepwise and numerical is both in the solution of Schrödinger's equation and in that solution of Newton's equation that we want to do. Now, why is the solution of Newton's equation nice for us? So again, I have my particles, and now they are red, all right, and they make some movement. Okay? So I look at my particles and I follow the particles for some time. I don't know how long, maybe picoseconds or milliseconds or nanoseconds, or whatever, we shall see. And I can do the trajectory numerically, so for each time, you know, at time equal 500, I know this particle is here and that particle is there, and so I'm happy. Now, maybe you already heard about this somewhere. When you solve Newton's equations like this, certain properties of your system are conserved. So when the system moves along the trajectory, particle 1 like this and particle 2 like this, some things stay constant. What stays constant? That's right, the momentum of the system stays constant if there are no interactions with outside. So if nobody from the outside kicks the system, then it keeps its momentum constant, which means if one particle moves like this, the other particle moves like that, and so the momentum stays constant. That's a nice feature, but there's another feature that is even nicer for us. Mathematicians call it the first integral. Doesn't mean anything, it's just a name. What stays constant? So the momentum of the system. So what is the momentum of the system, of course? Let's write it down. So what's the momentum? MIVI of t. And I sum over all I. So in my case it would be 4. And this is constant. And this is a vector. So actually it's 3 constant because Px is constant, Py is constant, and Pz is constant. What else is constant?
Mass.
The mass is constant, right? What else is constant? The number of particles is constant. I mean, particles do not appear or disappear. What else is constant?
Volume.
Volume, if I make it constant, I can make it, the particles can go in all space if I do not keep them from doing that. But you are right, at some point I will make the volume constant.
Energy.
Yes, exactly. The energy is constant. The total energy is constant. Now, for which partition function do we need total constant energy? Microcanonic. This is how we construct the microcanonic ensemble. We have everything we need. We can construct states, system move. We stop the system every so long, write down the position of velocity, have a new state, and the energy is constant. And on top of that, the momentum is constant, which we don't really need, but which is a nice thing to have. So we have all the ingredients now. We know everything that we need to construct the microcanonic ensemble. So we know how to do molecular dynamics. This is the secret of molecular dynamics. So, to sum it up, know the potential energy surfaces, know how to take the derivatives of the potential energy surface, so you get the forces, specify some initial condition, which is easier said than done, but you can imagine that you can do that. So you specify some initial condition, and then you get your trajectory by numerical methods. Okay, so how many steps? 4 steps. Know the potential energy surface, know how to compute the forces, know the initial conditions, know some numerical methods to get the trajectory, and then just get the trajectory. And the trajectory, this is what we saw yesterday. You remember my water molecules moving around? This was a trajectory. And this trajectory I can then sort of say I stop the trajectory every maybe 50 femtosecond or something like that, and that's a configuration, that's a state. So run the trajectory 50 femtosecond, write down everything. Another 50 femtosecond, write down everything. this will be my sample. Okay? What time is it now?
Nearly 2.
Nearly 2. So I have a little bit of time to tell you that in one case, however, I can solve these Newton's equations. Okay, there is one very special case, and special case means the forces are very special. So if here the forces, they are just the derivative of the potential energy surface. Okay? And the potential energy surface, that can be whatever it wants. It can be Lennard-Jones, or it can be Coulomb, and there are many others. It can be a Buckingham potential, and it can be Morse potential, and blah, 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 blah. It can be many, many things. Now there is one that we love so much, I told you, and which is the one we love so much? Which is the potential energy surface we love so much? All engineers love so much, and the spectroscopy love it so much, and it's sometimes a very good model, and sometimes a very bad model.
He said,
Harmonic potential.
Yes, right, of course, harmonic potential. Of course. So if the forces come from harmonic potentials, and you know the force from a harmonic potential, that's particularly simple, right? If my potential is proportional, let's say, to x squared, right? Harmonic potential is proportional to some variable square. What is the derivative? 2x. So it's linear. So the force, at least the modulus of the force, let's not talk about the direction, is proportional to x. And if this is so, Michael maybe will explain to you, you can again do some matrix calculations. This whole thing here, becomes a matrix problem. This is described in books about spectroscopy. And actually, when you use Gaussian, maybe you computed frequencies because this is built into the Gaussian program. It can approximate the potential energy surface by harmonic potentials. Whether it's good or whether it's bad, it's another question. The program does it. And then it does this rather simple matrix calculations, and it finds the vibrational frequencies on normal modes. So I shall not, I think we have no time, it's also not so very interesting to derive how this solution is done. You find it in books about spectroscopy. Michael, can you say it in a very few words?
Yeah.
I think we just look at the characteristic of the solution.
If you have, let's say, a molecule, and you have, let's think of a water molecule. That's maybe simple. And in the water molecule, we can assume that the atoms in the water molecule move, or the water molecule vibrates harmonically. That means the change in the positions of the atoms when it vibrates follows some parabolic shape. And so the trajectory or the trajectories, if you think of the different atoms, they are parabolas. And so everything is the same as Philip has shown on the blackboard maybe 2 days ago with some diatomic molecule when you had just one coordinate. There was the parabola of the energy. And now, however, we have 3 atoms in the water molecule. And the question is, how can we extend this one-dimensional case, which is so simple, to 3 dimensions? And one can write it down, but just in words. If you have this one-dimensional case of the diatomic molecule that vibrates, what is the formula for the vibrational frequency? Do you remember?
That's high school stuff, yes. So,
Yeah. So in this formula, you need one thing.
I forget about this, and I get the vibration frequency is what? Yeah, square root? Square root what? Square root 2?
Have pi inside.
Oh, forget about the pi's,
Okay.
it's only the important part. Well, the important part, of course, is here K, the force constant, right? You know how curved this is here. Does it look like this or like this? This is described by K. And remember the girlfriend on motorcycle problem? So the mass. Okay, and if I have 2, I have something that I call the reduced mass. If you have only 1, so if you have this problem and there's only 1, then it's K over M, where this is the mass. And if you have 2, it's the reduced mass. And the reduced mass you can compute as 1 over mu is 1 over M1 plus 1 over M2. So this is the generalization for 2 masses. And now we're looking for the generalization for 3 masses, 4 masses, 5 masses. And of course we get something that is similar to that, except that this becomes much more complicated.
And so it's a little bit like in quantum mechanics with the Schrödinger equation. In the general case, when we have more masses, well, actually with 2 also, but there we can make it more simple with the mu. We have a so-called mass matrix. The mass matrix contains, it's just a diagonal matrix which contains the masses. So in case of water, it would be 1, 1, 1, 8, 8, 8, 1, 1, 1, if we work in Cartesian coordinates. So 9 times 9 diagonal matrix. And in the denominator, in denominator is the mass, but above the denominator is the force constant. And the question is, what is the generalization of the force constant K? Well, that is also a matrix. It's the so-called force constant matrix. And the force constant matrix tells you how much does my energy move change if I move one particle a little bit and the other particle also a little bit, and so on. And well, we can think of Cartesian coordinates or internal coordinates. In internal coordinates, we have just the distances between O and H, and we can say the other things are 0 except the angle between H, O, H. So it's a 3 times 3 matrix with some zeros. But in the Cartesian coordinate system, it's more complicated, it looks quite ugly, but it's in the computer it's even more easy to calculate the result.
You see, the point is when you have if you have a triatomic molecule where the angle is not 90 degrees, right? If you move the oxygen atom, you will stretch both springs, right? Or if the angle is okay, I will not discuss the detail because there's also some expansion and it works only for infinitively small displacements or so. This Voskhod matrix, it takes care of the fact that when one atom is moved, maybe not only one spring is affected. Maybe it will change the length also of another spring.
And now we have these two matrices in the square root, and it's very easy to divide one matrix by another, especially if they are square matrices. So you can make the reciprocal of the of the mass matrix and multiply it with the force constant matrix, and then you get another matrix. And what is the equivalent of the square root? Well, actually there is a square root matrix, but it is not the correct thing to do. In this case, the equivalent thing of the square root is the eigenvector, eigenvalue function. So if you just calculate the eigenvalues of this matrix K divided by M, then you get the vibrational frequencies. And in our case, water has how many vibrational frequencies? A single molecule of water.
How many vibrational frequencies in water? Well, how many degrees of freedom in water? Altogether, everything. 3 atoms, 3 coordinates per atom, 3 times 3 makes 9. So 9 degrees of freedom. The whole molecule, how many degrees of translation? So the water molecule, X, Y, okay, I cannot jump, Z. So how many degrees of translation? 3. How many degrees of rotation? Another 3, 6. So how many are left for vibrations? 3. So we will find 3 eigenvectors and 3 eigenvalues. And I will look a little bit now at these eigenvalues and eigenvectors. So here's my water molecule. So I will get 3 vibrational modes. And I think spectroscopists call them Q1, Q2, and Q3. They are all 3 infrared active, so you can observe them. So if you put water vapor in a chamber and you do infrared spectroscopy, what will you observe? What have you observed? I'm sure you did it in the lab. At least the chemists did it in the lab. Well, you will find 3 absorptions. And you will find 1 absorption so here I plot the energy or wave number, centimeter. So energy in centimeter minus 1. So I have 1,000, 2,000, 3,000. And I will find 1 absorption here, 1 absorption here, and 1 absorption somewhere here, weaker usually.
So these are really the numbers that you get as eigenvalues from your force constant matrix. And if you take this Cartesian 9 times 9 matrix, of course you get 9 eigenvalues, but 6 are 0 because translation has vibrational frequency 0 and rotation has also vibrational frequency 0, and then you get 1600, 3500 and 3800 as the three eigenvalues that are not 0.
Okay, so we have 3 vibrational frequencies. Who can tell me what they are? Can you give certain characteristics of the vibrations that make these frequencies? Yeah, this one. So we have the so-called symmetric stretch. Let's use some color for the symmetric stretch. Okay, the symmetric stretch will be red. See, the oxygen is much heavier, but it has to move a little bit so that the center of mass does not move. Because per definition, a vibration does not move the center of mass. So it's some motion like this. Which frequency is this?
The 1500.
No, it's not the 1500 or 600. This is this one. This is the symmetric stretching motion of water when both hydrogens move in phase. Now there is one above, which is 150 or 200 wave numbers above, which I will make in this blue. So this one, which motion is this one? Bending? No. It's not bending. Now this is symmetric. If it's not symmetric, yeah, what could it be? Exactly. Anti-symmetric. So the anti-symmetric eigenvector, because what I plot here is the eigenvectors. The anti-symmetric eigenvector is like this. And you see the oxygen has to wag a little bit, again, so that the center of mass should not move. So, you know, when I do like this, both hydrogens move to the left, to my left, to your right, and so the oxygen has to move the other way. Has to be something like this. Okay, and the third one, of course, is the bending. So this would be so we have 3 vibrational modes, and these vibrational modes are orthogonal. Because if I take the scalar product of the 3 red vectors with the 3 gray vectors, I will find 0. Or if I take the 3 gray vectors and the 3, what are the other, blue vectors, I will find 0. So this approximation that we say we represent the potential energy surface, the very low part of potential energy surface, as harmonic functions. So we can do this matrix business and find these normal modes. This is very useful for spectroscopy, because this is how in spectroscopy you identify the motions of molecules that correspond to certain absorptions. And not everything is as simple as water. I mean, sometimes you have hundreds of peaks, and then you say, well, is this the NH, or is this the symmetric, or is this the anti-symmetric, or blah, 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 I don't know. And then by such calculations, you can identify your modes, or you can assign, the spectroscopy say they assign the modes. So they say the frequency at 750 wave numbers I assign to this and that motion. On the other hand, the fact that it is that they are orthogonal, these motions, means you cannot really do thermodynamics with them because they are orthogonal. And the fact that they are orthogonal means that will never be any energy going from one mode to the other. So if your molecule vibrates like this, it will never start vibrating like that, because there is no flow of energy between different modes in this very simple approximation. So normal modes are useful, but for certain things, and not very useful for other things, because they are orthogonal to each other. Energy does not flow from one oscillation into the other oscillation. Now you will find many, many papers where people compute these normal modes. I mean, people in biology find them very useful. People who do transition state find them very useful, because they look for the normal mode that has zero or negative frequency, because that identifies the transition state. And very often you want to, I mean, infrared spectroscopy is a fairly routine technique, so it's good and helpful to compare at least the surroundings of the minima of your potential energy function, and this is what is represented by the harmonic approximation, to compare that with experiment. You know, if your normal modes come out completely different from the experimental ones, then probably your potential energy surface is not good. What's the question?
The three eigenvalue come from the vibration, because
Yes?
when we consider the potential energy surface, the translation and rotation not change the energy, right?
Exactly. Exactly. This is why when you do this matrix business, you get zero frequency. So you know, you do a 9 times 9 matrix diagonalization, so you get 9 eigenvalues, but 6 are 0. Actually, it's a good test. You should really get the 0. And sometimes, for numerical reasons, you get very, very small numbers, like 10 to the minus 5 or 10 to the minus 6 or something like that. And because this matrix diagonalization is, of course, also done numerically, and so, you know, sometimes 0 is not exactly 0. But it should be much, 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 much smaller than all other eigenvalues that you get, which are the real frequencies.
Can I just very quickly get a picture on the screen
Yeah.
where we have this force constant matrix? So here you see some examples. I've just looked it up very quickly now. And of course the water molecule is such a typical model. And you have
Coming back. Don't touch it.
let's look at that. So that is the 3 times 3 matrix. And that's probably milli per angstrom, or I don't know, something like that. So the units of the force constants, they are force divided by length. And so that's the force constant if you just look at the elongation of one OH bond. And of course, the force constant for the elongation of the second OH bond is the same as the one for the first OH bond. So if you pull them apart, you need energy, and the energy can be described in energy as K times x squared, and that is the K. And for the angle, for changing the angle, you have this force constant, and you see it is much, I can copy the picture then to our Dropbox. That's much smaller because it's more easy to distort the angle. And then you have some off-diagonal elements. And what do they mean? They mean that the energy you need for changing the distance between OH1, the OH1 distance, depends also on the OH2 distance. And the energy you need to change the angle depends if your distances have changed. So these are the so-called off-diagonal, or the couplings between these internal coordinates, the R1, R2, and angle coordinate. And yeah, that's how it looks like. And when you do a calculation with a computer code like Gaussian, the program just calculates these force constants. So actually Gaussian does it in the Cartesian coordinates, and maybe sometimes then you can ask it to convert it directly into some internal coordinates, but that's not important. And let's look how that is. If I open again my HyperCam program, do I have it somewhere? Here I have it. I have just created a water molecule before, and I will repeat this thing so that you see how I did it. So I delete my water molecule. Okay, so you have at first to create your molecular system, or your many molecules maybe. So we say I create my water molecule. Normally you do that just by writing the coordinates, so not in this fancy drawing mode, but you write the coordinates because that's actually the professional way how to do it. Okay, now we have a water molecule. And then I can say, yeah, I want to calculate now the force constant matrix. And it's always more easy to calculate the force constant matrix from the optimized geometry. And why is that so? Yeah, that's so because it's assumed that you are at the minimum of this energy surface, and going to the left goes upwards, and going to the right goes also upwards. Otherwise you would get some, yeah, it would be possible, but not with this formula, with a complicated formula. And yeah, then we have the force constant matrix. If we say we want to do a vibrational analysis, and unfortunately I think I cannot show you the force constant matrix. It's in some file, but I don't know where to find it. But I can take the force constant matrix and make this calculation of the eigenvalues and the eigenvectors. And you see, maybe, yeah, I think you can see it. You get exactly what Philip has shown you. It's just
The scale is just the other way around.
It's just the other way around.
I mean,
You- you
spectroscopists like to put energy to the left and
You have
physicists
here-
put energy to the right.
You have here on the left side the high wave numbers. So you see here is 5,000 and here is 2,900. So that are strange wave numbers, but we don't care about that. So how does the highest frequency look like? Well, if we look at it, that's this.
It's a good rule of thumb. And there's a rule of thumb of spectroscopists that when you have a group like this, the asymmetric frequency is almost always higher than the symmetric frequencies. There are only very few exceptions. So when spectroscopists look at the spectra and make the assignment, usually they will start by guessing that when they have two which are close, like here, the higher one is the asymmetric one.
And you can explain it a little bit by the fact that the oxygen has to move less. Yeah, I think it's a correct explanation. Anyhow, so you have three vibrations, and they come from this 3 times 3 force constant matrix, which was a numerical matrix that we had before. And how does the lower frequency, one lower frequency look like? That's the symmetric one. And it's a little bit lower. And then we have the one that is very much lower, which is here. That's the bending frequency.
Here it goes faster, but that's the computer. I mean, in reality, it's only about half as fast, right? But here somehow it's the graphics that count, and obviously doing the graphics for this is easier, so it's faster.
Yeah, the reason why this is just not numerically precise is that I have just used a force field. I did not use some ab initio calculation, and then it's very, the numbers are not correct. I could use an ab initio calculation to get a force constant matrix, then it would be better. Yeah, and so that's it. And you might ask yourself, well, actually, why, if I have the force constant of OH and the force constant of the angle, why doesn't the OH one vibrate by itself and the OH2 vibrating by itself would then be some other vibration, and the angle vibrating by itself would be the third vibration? Do you have an idea why OH1 cannot vibrate just by itself. So something like if I would make it a tritium, then it would be maybe nearly so that it would vibrate by itself. But do you have an idea why in the water molecule there is no OH1 vibration, but always the other OH vibrates also?
Symmetry?
Sorry?
Symmetry of the OH.
No,
Yeah.
not really.
Yeah. But let's think.
I mean, you remember Michael's force constant matrix and these off-diagonal elements? Even if I make all off-diagonal elements 0, right? So there is no potential energy coupling between OH1 and OH2. Potential energies are totally independent. I will have this phenomenon that in the water molecule, the motion of the two H's are correlated. They are either in phase or out of phase. So if it's not in the potential energy, where could it be? If it's not potential energy, it's kinetic energy. People call it kinetic energy coupling. And it comes from the fact that, you know, when OH1 vibrates, the O also moves. And so the other OH knows about the motion, just because the oxygen moves. And to test this hypothesis, you can make the oxygen very, very heavy. And then the two OHs become independent. Because then the oxygen does not move anymore. So we have potential energy coupling, which means that the potential energy changes for OH1 if OH2 is elongated or compressed. And there is kinetic energy coupling that comes from the fact that this atom that is linked to the two other atoms moves.
So the water molecule would be a strange thing if the OH1 would move alone. It would vibrate in space. The center of mass would vibrate in space. And of course, that's not possible. You cannot, if it is not fixed to some position, it cannot just vibrate in space because there is no force that goes backward. So there must be a balance, that the center of mass must be fixed or in a constant motion, in no motion or in a constant motion. That's the thing that prevents the vibrations to be separate. You have this mixture of the vibrations.
And in more, I mean, a molecule with more atoms, then this becomes, I mean, this coupling between the various modes becomes more complicated. Because if you use methane, you have 4 CH bonds, and then you have one vibration which is totally symmetric, where all H's move out together, but then you have many asymmetric, and there are several possible asymmetrics. One group goes like this, and the other like this, and some of these are what is called degenerate. So that's really what you study in spectroscopy.
So now I have done some terrible thing here. I have replaced one hydrogen by plutonium. Plutonium is very heavy. And you see, indeed, now the plutonium does not move, only the OH1 is vibrating. But that is just because of the different masses. So the vibration of the OH1 still keeps the center of mass constant because of the heavy plutonium. And you would not need plutonium, it would be smaller mass would also give the same picture. Yeah, and the second one would be this one where only the plutonium oxygen is vibrating, but the OH1 is just doing nothing. But in the real water, I mean, you are kind of right, because symmetry means H mass 1 is equal to H mass 2 in some sense. The vibrations can only work if they are mixed. So that's just a illustration.
So sometimes people use HDO because then the modes are already more independent. Right? Because the OH, that's still roughly 3000, but the OD, that's much slower because the D mass is twice the H mass. So it's some square root of 2 slower. So you have a molecule where one vibrates roughly at 3000 and the other one vibrates roughly at 2000 something. And then the coupling is again completely different, much weaker, and the oscillators OH and OD are almost independent. And so people have used it in experiment when they wanted to see the reaction of only one OH without the coupling to the other OH.
So the deuterium has twice the mass of the hydrogen. Why don't the people use tritium, which has even a higher mass?
What's the trouble with tritium in the lab? Why do the stupid Chinese make such a noise that now that the Japanese release the water from Fukushima into the ocean? What do the Chinese claim? Which of course is wrong, but Mr. Xi Jinping is not much encumbered by truth. Just wants to make noise. So what noise does he make? Radiates, right? He says there's so much tritium in the water, it's radioactive. Now, tritium is radioactive, but there is so little in the water that there's probably more in your lake, Vistek. Okay, so tritium is radioactive, so deuterium is easy to handle in the lab, but tritium is complicated to handle in the lab.
So it is not worse to make the isotopic experiment with tritium.
Okay, so let's have a break. I suppose it's about time. And then it will be question and answer.